Hi, everyone. So my name is Francesco Guardiani, and I'm here today to introduce you microservices with Restate and Kotlin. I'm a software engineer working at Restate, working on the global execution engine core, which I'm going to show you in a minute, and on the developer experience. I'm based in Germany, but you might have guessed it from my accent. I'm from Italy originally, and yeah.
I'm Giselle. I also work for Restate, and I'm a developer advocate.
All right, so I want to start this presentation by asking you to look at this 4 relatively simple lines of code. Let's say you need to build a food ordering app where the user can only order pizzas because that's what you order. And let's say that when you process this order, you need to do a payment. So you need to process a payment. And then afterward, you need to execute the delivery. Now, when you think about this, you think about this in very linear terms. You need to do this, and then you need to do that. But if you implement something like this, just as this simple code, you will start stumbling on so many problems, so many errors, so many failures. For example, what if the payment fails and you need to retry after a couple of seconds? Or what if the payment fails, but you actually need to retry after 1 or 2 hours because you cannot retry immediately? Or what if the payment succeeds, but then the delivery fails? So you need somehow to roll back the payment. You need to give a refund. Or what if the payment succeeds, but before you execute the delivery, actually just this service, this code crashes? It can be for whatever reason, network failure, power outage, doesn't matter. Or, for example, what if the user is really waiting for his pizza to arrive? So he's pressing many times, please check out, please send the pizza. So how do you solve all these problems? Well, right now, if you need to make this service fully resilient, what you would have to do is, well, to bring in many different endpoint solutions. For example, you will need to bring in a session key value store to somehow keep the session. Or maybe you will need to bring in a message queue like Kafka, SQS. It doesn't matter which one. For example, to connect the different services in a way that you remember what you have already done, and the services can be connected in such a way that the message from one service to another doesn't get lost. Or maybe you bring in a workflow orchestrator, something like a Camunda, AWS Step Functions, it doesn't matter. One of those that give you a way to actually track your execution and see where you are in your execution in a single point. Or maybe you also bring in a scheduler, in particular for the case where you need to retry, but you can't retry immediately. You need to wait to retry for some time. Well, in that case, you can't just do a thread sleep of 2 hours. Or maybe you bring in some logic for doing manual retries. For example, you bring in a Resilience4j, one of those libraries to do retries. Or you bring in some recovery logic that is custom-made. Or maybe, you just don't solve some of these problems. Sometimes we talk with some people about durable execution, and they ask us, and they say, what do you do if in that case you double bill the user? And they answer, well, in that case, it doesn't matter. We double bill the user twice. Worst case, they send an email to the support and we refund them, which, in some companies might work, but definitely not everywhere. So, when you start then collecting all these different solutions all together in your microservice architecture, well, you end up in something like this. And, well, this is real. I remember very vividly, first the conference I was, this talk about microservices. There was this company I was building, was a backend for mobile games, microtransactions, that type of thing. And, resiliency matters in that case because if a user does a microtransaction to buy coins in the game, they don't have to get lost. That's quite a problem. So, in their case, like they described this flow of the microtransactions, and the presenter ended up in really a graph that looked like this. So, this is real. And what's even more real is that after you actually make the architecture so complicated, you'll probably also not solve all the problems. You're going to have race conditions between all these different systems. You're going to have inconsistent state. You're going to have a duplicate request that sometimes you need to solve, and not all these systems have the same way to solve the problem. Multi-write problems, request timeouts. And request timeouts in particular, when you can't control the timeouts of these different systems, can easily cause cascade failures. So yeah, we asked ourselves, well, can we do better? Is there something we can do? And even more interesting, isn't there some core building blocks, some primitive, something very fundamental that is missing, on which on top we can actually build everything else? And for us, the solution to this is durable execution. So durable execution, as the name implies, is durable execution. So means that the state of the execution, what happens in your execution, the steps that you do, gets somehow recorded and gets stored durably. So if you have any sort of crash, power outage, bug, doesn't matter, you restart from the point where you were, and you want to execute what you have already done. Now, durable execution as a concept is not something that we have invented in the last year or two. It's something that has been around for a very long time. Workflow engines have been doing this for a very long time. But in the last years, different projects developed new and interesting ways of doing durable execution. In our case, we took the approach so-called log-based. The idea is, well, very simple. In a log-based durable execution engine, what you do is that you put the engine between your clients, for example, the browser, the mobile app, the desktop app, doesn't matter, and your service code. And your service code needs to be written with a library that, of course, understands the durable execution engine. And when you send requests to, well, in this case, it's Restate, of course. And Restate internally will prepare this log data structure for this specific invocation. And from there, it will forward the request to the order service. Now, the order service does stuff, does the payment, and this payment gets logged. So we store in our data storage the success of the payment. And then this goes on and on. So same for delivery. And then when you get a response, the response gets forwarded back to the original client. Now, let's say you have a crash. Crash happens after you do the payment and before you do the delivery. Well, in that case, let's say the service crashes. Or actually, let's say Restate crashes because, you know, Restate runs on hardware, and hardware needs power. Power sometimes goes away. Or, well, also Restate is built by humans and not by AI, so there are bugs sometimes. And yeah, what happens in that case? Well, in that case, when everything is back up again, Restate will figure out in its internal storage, well, I have some stuff that I need to complete. I have some invocations that I need to run to completion. And for doing that, it will send a request to process order saying, hey, look, you need to resume this invocation, and you need to restart from this point. So this is everything that I've done and that I know so far of this invocation, but you still need to do something. And in this case, what we have recorded so far was the do payment operation. So after that, we will restart from delivery. The delivery gets logged, and then the process goes on and on as before. Now, I want to show you a very quick demo of how actually durable execution works in practice, so you get a bit of an idea of how this works. So let's say we have, this is the very same code that you saw before. Right? Yeah. This is the very same code you saw before on the left side. Yeah. You have do payment, delivery. There are just two new things. First, we have wrapped this do payment and deliver inside those functions run block, which I'm going to explain in a second what it does. And then I have also introduced an artificial failure, just doing check faults, effectively. Now, let's say we start this service. Okay, so just run main, simple. And we send a request to it. To send a request, we just do simple HTTP request with JSON payload. Very simple. And yes, so in a service that would not run without a durable execution engine, your expectation would be that when you reach check faults, just fails and gives you back the error on the client. But this is not what's happening here. What's happening here is that the HTTP client over there is waiting to have a response. And on the other side, you see two things are going on. First, at the beginning, we logged do payment. So this do payment function just does print line, so very simple. And this function was executed, so do payment was executed. But then after that, we stumbled on the check faults, right? And you see that the exception gets logged and so on. But then this gets logged many times. and you don't see anymore the do payment. You have seen it. You have seen the logging of do payment only once, but at the same time, you are seeing this error being retried multiple times. That's because the durable execution engine is trying in a loop to run this to completion. Now, we can use some introspection tools. With the command restate invocation ls, we just log, essentially tell me what is running right now and what's going on in what's running right now. And in this case, this command is telling me, so every invocation has an invocation ID attached to it that is unique. And then it tells me, yeah, this request was sent to food ordering process. It's baking off, has been retried 13 times. And the last time I got this error, there's a Java illegal state exception. And if you do restate invocation describe, you get something very interesting. You get the same screen as before, but you also get this thing here, invocation progress. This invocation progress here is telling us what has been done so far. So far, the invocation was created by the ingress, which is just the internal component which you send request to. And then the payment was done. So I processed the payment, but after that, I'm baking off. So I'm stuck in this retry loop, and I don't know what to do next. Now, let's say we just stop this service. First of all, when we stop the service, you're going to see, if we do describe again, you'll now see that we have a different error. It's not anymore the Java illegal state exception, but it's more like, look, I cannot connect to the service. Where is the service? I don't know what to do with it. Now, let's fix this bug in our code by just commenting the check faults. And let's run this again. And guess what's going to happen? Give it a second, 10-second back off time for retry. Should have made it shorter maybe for the demo. And yeah, we got the logging of start delivery. So the invocation restarted just from the delivery block. And it skipped the payment block, because the payment block was already done. So this is the high-level idea of really what durable execution is. And from here, we can extend to many, many other things. Now, behind the hood, what the durable execution engine is doing is that, as I said, it's storing all those different logs for all those different invocations. So when you send a request to restate, this request translates to an append to our internal storage layer that is just, we call it the big restate log. It's just a log data structure. And from here on the other side, we have a state machine that reads from this log and sends request to Kotlin, to service code that can be Kotlin. And every time there is some progress in the service code, this is sent back in the big restate log. So it gets appended and gets processed and so on and so forth. And I don't know who of you worked on EDAs and on Kafka, state machines and stuff like this, but if you have done that, you will probably recognize this architecture, because at least for me personally, I worked in some companies in the past where I've done something fairly similar to this, where you use essentially Kafka for your persistence of commands, and then on the other side, you have this state machine that just reads the events and so on and so forth. But in this case, we kind of abstracted that and made it such that you just write sequential code, and you don't have to think about these problems. Restate itself, the way it works is that it's just a single binary, because it has internally this persistence layer that is replicated using Raft consensus, and it's based on RocksDB. It means that it's essentially battery packed. You don't need any database to deploy, anything like this. It's open source. It's built using Rust, the runtime, but then the services, you can write them, of course, in Kotlin. It's built with this low latency focus in mind, so we try to meet those use cases that are more user interaction use cases. And you saw it. It was running on my machine. It works everywhere. Eventually, it works on your local machine. You can deploy it on-prem. You can deploy it on a Restate Managed Cloud. And yeah, so now our journey here was that we reached the point where we said, OK, we have durable execution. That's pretty cool. That's our foundation. But can we do something on top of it? Can we, from here, create the foundation for adding other features that you eventually need for building microservices? So yeah.
Yeah, so as Francesco showed, what we have done until now is basically execute a single function, so a single handler, the do payment delivery one that he just showed, but in a microservices architecture, this is just one small part of the entire application, right? We have several services communicating with each other in all sorts of ways, functions calling each other. For example, a request response call, or a call where you don't want the response to come back, so basically like a message queue where you just want to send a message. Or even things like schedule a task for later on, like execute this function tomorrow or next month. And we were wondering if we can actually use the same foundation also for this type of communication between services. So what you get then is basically the Restate server, which sits in the middle of all services, becomes like an event broker, a bit like a reverse proxy that turns the services that sit behind it into durable handlers or workflows or objects. And what happens is when one service calls another service, that call gets executed in the same way as what we showed before. So the nested calls from service to service to service, they all are guaranteed to run to completion. And this idea is actually pretty interesting, because if you then look at the position of this server, it knows all the invocations that are ongoing, it knows whether they are finished or not, it knows what the final, like the response was of them. So something you can add super easily to this is idempotency, because if you attach an idempotency key as a header to your request, Restate can easily see, this is the same one, so either latch on if the invocation is still ongoing, or return the previous response. So you basically get idempotency for free in that sense, by just putting Restate in front of it. And for that, you actually don't even need to use any of the SDK features, what we were showing. Just by putting that in the middle, you get that. All right, so now we have communication and execution. Then there's one essential part missing, and that's actually state. So the thing we were showing here, process order, you can imagine you have, for example, some state machine that you want to keep track of. For example, the order goes through the states new to paid and then to delivered. These are the type of variables that you want to be able to access from several executions. So several functions and handlers could be operating on them. So how do we marry this into this durable execution pattern? Basically, what happens is the log also becomes a bit like a key value store, or has a key value store next to it. And what happens then is if a request comes in, the state that is needed to process that request is attached to it, and like that, it's forward to the function. So when the function gets called, it already has the state that it needs to process the request locally delivered together with the request. And then as the handler executes, it mutates that state, or maybe just deletes it at all. Those state changes can just be added to the same log that we showed earlier. But there is one thing there which is then still necessary in order to make this actually consistent, because as you can imagine, if multiple handlers are executing on the same state, you don't know anymore what is actually the final state. So in order to solve that, when you want to use state in your services, we call it virtual objects. And what that means is, for a virtual object, we create a single object for each unique identifier of it, and that object has a state store attached to it, basically. And every invocation to a single virtual object gets sequenced. So an object has state, and every invocation that goes to it gets executed one after the other. So every invocation can do as many state changes or whatever it wants, and then the next invocation will just get the latest version of the state. So you basically have consistency across all the aspects of communication, execution, and state. So if we take a bit of a look at a simple example of a virtual object, this is, for example, a driver service. Imagine that every object we create of this service is another driver, which has a unique identifier. And that unique identifier basically identifies the object. And a driver can, for example, have a location, like where he's driving around right now, and we want to update that location regularly. So what you see here is a driver service, and the update location function sets new locations in the state store. And then when we want to know where the driver is, we can call the get function, and it returns us the state. All right, so what can we actually do with this? So if we have all those things together in one log, that actually also gives us resiliency across all those aspects and consistency. So that makes it much easier to implement code than having many different point solutions and needing to write actually the code that keeps stuff consistent across all of them. So basically the glue between all those point solutions that we were talking about earlier, like the key value stores and message queues, etc. So what we get is we have the durable execution within a handler, then we have the durable promises and RPC for the communication part between handlers, and you have the state across the different executions of handlers, so they can store things. All right, so the first demo we showed was a pretty simple demo. Let's now look at how far you can actually go with this. So this demo will be a microservices architecture where we implement a food order processing example. So the idea is you have a UI where customers can select some things they want to order that gets translated into a request to an order workflow. And that order workflow is the orange box right on top. Does the normal stuff like triggering the payment, then asking the restaurant to start the preparation, and then doing the delivery. And for the delivery part, we have the lower part of the boxes here. So we have the cooperation between a few services. There's a delivery service which keeps track of where a delivery is, and a driver service which keeps track of where the driver is. And for that driver, the updates will be streamed over Kafka. So imagine the driver is driving around and has a mobile app. That mobile app streams location updates onto a Kafka topic that we will include in the demo there. Let's first have a look at how this is implemented in code. So here is my order workflow. So it's a virtual object. Here we see some references to the state that I can access. And then after that, you see the implementation of the process function. So the process function gets two things delivered to it. Object context, which is basically the connection to the SDK. So every time I use CTX in the code, basically that leads to an event sent to Restate. And the request, which is what our customer wants. So the first thing we do here, we have a few patterns that we implemented in order to process the order. The first one is the payment, so that's these two lines here. If you are aware with payment infrastructure, usually providers such as, for example, Stripe allow you to attach an idempotency key to your requests to avoid that you do payments multiple times when you send the same request twice on a retry. So what we do here is we first generate a unique identifier, an idempotency token. And what happens when this gets executed is that idempotency token becomes a log entry. And once this is executed and it is a log entry, this will be the same on every retry. So this will be a stable token across all the retries, so then we can do the payment and supply the idempotency token to it. So let's run this. There is a little very basic UI where we can order a cheeseburger, for example, and then press
pizza.
and then press checkout. And then if we look at the log, we should see that this starts executing. So if we scroll a bit up, we see here the payment failures. That payment client.charge fails every 50% of the time. But so here we see the idempotency token printed right before it tries the first time. So it's idempotency token 46E. And then if we look a bit further at where the retry is taking place, then we see that here it will try again with this same idempotency token. So what happened is it just got it from the log instead of generating a new one. And then the payment is a success, and then we continue our workflow. So all right, now that the customer paid, we can go over to the next step. So this is an example of timers. So you have communication, but you can actually also register timers in Restate. And you can use those timers either to call another service with a delay, so basically send a message and attach a delay to it, or to just let a function sleep. And in this example, we let customers order something for later on. So for example, I want a pizza at 7 o'clock in the evening. What happens is this will just block until 7 o'clock in the evening, and then it will continue. And if crashes happen in the meantime, it doesn't matter because we just recover from the log. And if no crashes happen, then Restate will see, okay, it's 7 o'clock, I have a timer here that I need to fire, and it will invoke the service again. So let's try this out. We can order something for a bit later. For example, chicken wings in 15 seconds. If we now press checkout and go to the CLI, we can have a look at the invocations that are ongoing. Okay, so there on top we have the invocation that is right now happening. If I then describe this invocation and copy the ID, then I should see, okay, I was a bit too slow for the sleep. I was slower than 15 seconds, but actually the first one should show until the sleep, and then if I execute it again, you see the rest of the journal. So first the payment, then the sleep, and then you see the rest of the workflow. So this is a slightly more complicated log here, but it's the same principle as what Francesco showed. You see everything that's been executed. That awakeable there is the next thing I will show, which is a callback pattern. So, all right, we did the payment. We waited until the time where the customer wants his order. So the next thing we need to do is ask the restaurant to start preparing the food. So the way that works is we want to send the restaurant a request to start the preparation and let us know when it's done via a callback. The way we do that is we generate an awakeable, and an awakeable is actually two things. It's an ID and a future. And the ID is the thing that we send to the restaurant, so restaurant prepare and we supply the ID, and then we wait on the future to be resolved. So this part will block until the restaurant has delivered that ID back to us, basically. And that can be in an hour or in a month. That gets also durably stored in the log, and Restate is the one that will keep track of those like durable futures, let's say. The rest of the workflow is, I will skip over that because it's, again, more awakeables. Then maybe the final thing to show is how you can just call a service in a normal way. So if one service calls another service, we have like generated clients for that. You can send a message by calling the client, specifying that you just want to send it. If you don't use send, it will be request response. And like that, you can call the services of other services, the functions of other services, sorry. All right, now let's go over to a small example of a virtual object. So the one I showed in the slide was the driver service. This is basically a slightly more real implementation of that one. So it's a bit like a driver digital twin. For every driver out there, there is one object of this service that keeps track of his status, so whether he's working or not, which delivery he's currently doing, and the location of where he is right now. And this location is the thing that, when I show the diagram, is the thing that gets updated via Kafka events. So with the mobile phone of the driver, updating the location regularly. So if we go down to the function which does this, it's this one. Then we see again, we get the object, context, and the location. Then we set it in the state, the new location, and if that driver is doing a delivery, we also update another service. But so one interesting thing to show or to note here is that this is connected to a Kafka topic, but for those of you who have worked with Kafka in the past, usually you would see something like a Kafka consumer and a loop of polling a topic and subscribing to the topic, then going through each event and committing the offsets. So there's a bit of like boilerplate code you need to write in order to read from Kafka. And all that boilerplate is basically pulled out of this, and Restate takes care of that, because Restate is the one subscribing to Kafka. For every event that arrives, it will push it to the object, and it will maintain the order per key. So Whereas in Kafka, for one partition, you have several keys that map onto that one. Here, you basically spread that per object, so per key. And you don't need to do any of the management in your function. So for every Kafka event, it basically pushes the event to the function, and the function doesn't need to do the polling.
And also that impotency as well. Yeah.
Okay, so that was the code example. Let's have a look at maybe what this gives us. Maybe one final thing to note here, if you look at the workflow that I just presented, it looks like fairly simple, readable code, right? Like it's fairly sequential, it's almost like just the business logic. You don't see any retry loops, you don't see any recovery logic, you don't see connections to several systems. It's basically almost like a stateless function that just executes some steps and sends back what it has done via the SDK. But this works fully resiliently. It can fail at any point in time. It will always end back in a consistent state with consistent key value pairs connected to where it was in the execution, etc. So that's a pretty powerful building block to build resilient applications, basically. As a small summary, so what did we show? So a durable executed function without the retry logic, but also the communication side, timers such as sleep or calling other services with a delay, request response, but also async messages, so what you would otherwise use a message queue for, things like workflow orchestrators, cron jobs. And our front end used the idempotency key, so if the user presses the checkout button too many times, we can never get in a state where we deliver orders multiple times. For the virtual object side, we were able to just store that in the log together with the execution, so we don't need consistency and concurrency guards to avoid that we get into inconsistent state, which will be hard to fix. All right, so if we take a look at this idea of basically being able to restore a service to the point where it was before it crashed, then you can actually also use this for some other use cases, because if you can always bring a service back, then you can also just let it crash whenever you would want. And one use case where that could have some benefit is for serverless and function as a service platforms, because there you pay for the execution time. So for those of you who are not so well acquainted with it, for example, AWS Lambda, you deploy a bit of code, like a function, and you only pay when that function is executing for a request. When it's not executing anything, it doesn't exist, it's suspense, and you don't pay. But when your Lambda function does things like sleeping for a long time or waiting on that restaurant callback, then you pay for that execution time. But what you can do with durable execution is basically every time that Lambda function bumps it onto a point where it needs to wait, you let it suspend, it goes away, and you let Restate or the durable execution engine take care of the waiting. And then when there's a response or when the sleep has finished, it can just send over the log and the Lambda function continues where it left off. So that lets you actually build things like workflows as code on Lambda and benefit from a more efficient execution. In some way, you can also look at it as if it makes any function in your application a bit like a low latency workflow. Workflow orchestrators traditionally have a bit the connotation that they're more for like jobs where you don't care if it gets executed exactly now. In 1 second is also fine, or in 2 seconds. But that means it's not really usable for latency sensitive parts of an application. But so what you can do with durable execution is almost use workflows all over your application, because everything executes in like blocks that don't get re-executed, but does get retries, recovery, etc. And this also allows a bit more a gradual adoption of a tool like Restate. You could start with one function in your application, which is a bit like the orchestrator, make that one durable, and just leave the other ones as normal applications, normal services. So that gives you a bit more like a gradual approach to adopting durable execution. Because all the services we actually show, they just run like normal Java services in Docker containers or where you want to run them. They don't run on special workers or something. So that lets you implement things like, for example, infrastructure provisioning, like use cases where you have a lot of retries. Like you retry until another resource is finally up. Or workflow interpreters, where you have very dynamic paths that you want to follow based on what a user selects. And this extends into the microservices orchestration space, multiple function services, but then resilient, consistent, and scalable. For example, I want to write to a database, then to another database, then send an email, and make sure that everything gets executed sequentially, one after the other, and that I'm sure that it runs to completion. I showed the example of event-driven apps, so lightweight, flexible event handlers, where you can, for example, if you get an event on Kafka, want to execute a workflow, a bit like a transactional processing on Kafka, as opposed to tools like Flink, which are more used for like big data, stream processing, like aggregations across events, etc. And then finally, you can also do things like more like scheduling a cleanup task. For example, an e-commerce application where you keep track of a shopping cart in the state and you want to clean up the state after 15 minutes if the user didn't buy it. So all these kind of use cases. All right, then a bit of a summary before we end. So what we showed is basically resilient applications via a few different building blocks. So the first one was durable execution. So functions and services with the handling of retries, recovery, and idempotency. Then we extended that to communication, so to RPC and futures. So communications across services, processes, and time. And then finally, we showed that the integration with state, so via virtual objects, where you can also add key value state to your object and have concurrency guarantees that it's always consistent. So in the end, those things basically give you something like a distributed durable version of building blocks that you probably are already using in your architectures or infrastructure. All right, that was it. Thank you for listening to us, and